Hello, everyone. Good morning, good afternoon, good evening. Thank you for joining from different and multiple time zones. My name is Fatima Mustafa. I am an adjunct faculty at Texas A&M in San Antonio, Texas. I'm also a coordinator for a couple of projects at the International Union of Applied Chemistry, the IUPAC, the Global Women Breakfast, as well as the Word for Chemistry, which is why I'm here today. I'm excited to host this webinar to talk maybe about a topic that I think it's never been discussed in details in previous IYCN events, which is about the digital IUPAC term and the tools for digital research culture. I'm thrilled to be joined by a couple of specialists in the cheminformatics domain, Leah McKeown and Ian Prono, which I will introduce shortly. First of all, let me acknowledge the ChemVoices platform, which actually gave us this opportunity to be here today to discuss this topic. So a special thanks goes to Dr. Laurie Ferenc, who facilitated this event. ChemVoices is actually a partnership between the IUPAC and the International Younger Chemist Network, the IYCN, that was created a couple of years ago to showcase the talents of younger chemists and to give them a platform to discuss their issues. Now it became a very well platform for the IUPAC of communication. So in this webinar, as I told you already, we're going to be talking about the digital IUPAC era and term that maybe have not been discussed before. Personally, as a younger chemist, I have been involved heavily in the IYCN previous activities, and I got to know more better about the activities of the IUPAC. I never heard about the digital IUPAC term until last year. So, for example, terms like INSHI, the chemical identifier, I got to know about it just 1 year ago. It was an exciting topic for me to also use this opportunity to let my fellow younger chemists know about these existing tools that might help them in their research data management. The IUPAC has many efforts of transforming existing standards, chemical structure, and data into the digital form, meaning to be machine readable. I hope this webinar is a place to you to get introduced to this topic and to learn about how to implement these in nowadays research environment. We have prepared a bunch of questions, so it's going to be entirely a Q&A session, very engaging. You are also invited to ask your questions, so feel free to add your questions in the question box. We will be happy to address them while we are having the conversation with our guests, as well as towards the end. And if we don't have enough time to do that, we will also be happy to follow up later. All right, so let me introduce our first guest speaker, Leah McKeown, who I really consider her as a very passionate cheminformatic person. I work closely with Leah in the Word for project. This is how I got to know her. Leah, she has her background, educational background is a combination of chemistry, biochemistry particularly, and library information science. So she has a master's degree in biochemistry from Cornell and a master's degree in library science from Emporia State University. She is working currently as a librarian at Cornell University, supporting the research community over there. She is very highly active in international research data communities. She is the founder of Chemistry Research Data Group and the Research Data Alliance. She is also currently chairing the Committee of Publications Cheminformatics Data Standards at the IUPAC. I'm happy to have Leah with me here. Thank you, Leah, for preparing for all of this and being here today. Our second speaker is another dedicated cheminformatic specialist, Ian Prono. Ian Prono has a cheminformatics educational background. He has a chemistry from Durham University and a PhD in information science from University of Sheffield. He works at the Cambridge Crystallographic Data Center, the CCDC, since 1993. He is currently the Director of Data Initiative, and he's also very heavily active internationally and nationally, and participating in multiple global initiatives, such as the Research Data Alliance, the International Union of Crystallography, the INSHE Trust, and the IUPAC as well. He is currently the lead of the Word for Chemistry sub-project on reporting guidance. Thank you, Ian, again for being here. So before we get our conversation started, we have a first poll for all of you. If you would like to introduce yourself and let us know more about you, how do you best describe yourself? Are you a younger chemist below 35 years or within 6 years of your last degree or training? Are you a chemist or are you a chemical data user but not a chemist? So I'll give you a few seconds to answer this poll.
All right, we're going to close the poll in 3, 2, 1. Closing it now.
All right, so let me share the results of the vote. Thank you, Lori. So we do have 26% of younger chemists, 41% of chemists, and 33 people of chemical data users, where we have like almost similar contribution from all of the categories. So thank you all for being here again, and I hope this opportunity is good for you to learn new things. All right, so this is our first question, and it goes to actually Leah, and I know Leah has a strong interest in chemical data history research, and she got involved in one of her first experiences working and researching IUPAC archives 20 years ago when she got a sabbatical year at the Chemistry Heritage Foundation back then. You worked, Leah, with archives, and I'm excited to learn more about how has this opportunity actually enabled you and others to envision the digital era of the IUPAC.
Thank you so much for the question, Fatima. There it goes. Whoops, I think it's kind of skipped ahead. Can we go back a couple slides? I haven't touched anything. There you go. Okay, great. Thanks so much. I think there might be a little delay, so we apologize in advance. All right, so as Fatima mentioned, I had a sabbatical and I got to spend it at the Chemical Heritage Foundation, which is now called the Science History Institute. It's in Philadelphia, and it holds archives from many chemical organizations, including IUPAC, including also the Institute of Scientific Information, which is the core of what many of you may now know as the Web of Science. So I had a fellowship supported by the Institute of Scientific Information. The reason I was there is because just over a decade ago, the Physical Sciences Library at Cornell closed down its stacks and turned into a digital-only library. And when we were having discussions with the scientists supported by that library, which are primarily chemists and physicists, they had sort of two questions. You know, one, how are we going to make sure that that we can publish in a digital way, right? I mean, you know, if we have to use online information, how does our information get online? And then the second thing they said, well, and if we have to do that, how can we make the workflow to do that much easier? You know, we have a lot of different little software pieces and data everywhere, and it's just very confusing. And so that was the challenges we had. And I've been working with those scientists over the last decade or so on their workflows. But meanwhile, on my sabbatical, I also just thought to study what's the history that chemistry has. You know, even 10 years ago, we had SciFinder, we had ChemDraw, you know, we had many programs that we're using. You know, how did those come to be? How do they work kind of under the hood? How do we need to make sure those things can work in the more networked environment of the internet? And now we have the cloud. So that's what I did. I set up this symposium. This book is actually a summary of a symposium that was run at the American Chemical Society in 2012. It was a great time. because we were kind of at this turning point where we could invite colleagues in chemical information and chemistry database development fields who'd been in the field for 30 to 40 years and had seen a lot of transition. In fact, actually on the cover there, you can see a punch card. One of my colleagues in the book had started off his career as an innocent young librarian at the University of Zurich using punch cards to do structure searching of all things. So this is what we did in the symposium, is we sort of thought about how we work with chemical information in an online context up until now, and where we think the future might be going. So that was really fun. That was 2012, so just over a decade ago. Fast forward to now. Go ahead and let's see. I think I can do this. We're testing the.
I can do that.
Yeah, go ahead. There. I think this is a little slow if I do it. So at that time, and even still today, our traditional reporting practice for much of chemistry data looks like this. And this example is from spectra data. These are actually data from some labs that I've supported at Cornell. The data gets published in your final paper and it's embedded in your PDF, it's in your SI, and that's also a PDF file. A lot of your structures and your figures are static images. If anybody comes along and wants to read those or search that compound or something similar to a structure search, substructure search, they have to redraw that in SciFinder or wherever they're searching. And it's just a lot of steps to do that. Next slide, please. So that was the first question about how do we get our data more usable, right, for others. And then the second question they had asked me was, well, how do we make our workflow more efficient? So if you think about your spectra data, you make your observations, and then you have the instrument that's making the measurement, and then you have some analysis software, and then you might process this further, and then you put your supporting information together, and then you assemble all that, and you submit your manuscript. It's a lot of steps there. Often, sometimes you can import and export between programs. Other times, you might export something and then you kind of hand key your peaks back in when you're kind of typing up your supplementary information. You may have multiple steps there where you're kind of going back and forth. That's very inefficient, and there's a lot of potential for losing contextual data, typos, all kinds of things. And then at the end, you end up with these static figures, and people would have to look very closely at your spectra there to really perceive if there's any interesting smaller peaks that they might be interested in, in your characterized sample there. So it's really just not as efficient and usable, considering that all of that data came from instruments and went through software that are actually utilizing digital files. So why are we kind of taking this back into an analog format that's hard, that's hardened right? Without being able to use it? So that's the challenge that I was put to by my scientists, and that's what I've been working on for the last decade, on how to tackle that and what's involved. Go ahead, Fatima.
Yeah, wonderful. So with these tons of research and publications and hundreds of thousands appearing every year, and as you mentioned, they have so many elements and pieces incorporated there of spectra and so many pieces of data. How does adopting best practices of research data management before, during, and after the research publication is affecting research publication? What are the challenges and what are the needs in your opinion, Leah?
Lots. Go ahead to the next slide and we'll dig right in. Okay, so these are fast forwarding a few more years from my original work. 2015, there are a couple of studies done, actually taking a look at data that had been published in a lot of different chemistry articles and other disciplines. And you can see in the top figures there that almost 75% of the articles they looked at that were chemistry related actually refer to their data in their article, so that's good. But very, very, very few of those actually included data files that you could download and use. And I think that's probably pretty similar today. I wouldn't be surprised. And in the bottom figure just reinforces what we were already discussing, that most of that data, when you actually took a look at it, is published in the PDF, in the text, in figures. Those are all hard to get out. There are text mining technologies these days, but that's kind of rough and ready. It's it's not very systematic. They have to troll through things. Again, they might lose contextual information mining through the text. So, you know, it's not really clean. And again, these data are all generated by instruments and through software. We should be able to develop some workflows that string these together. You want to go ahead? Okay, so and then another thing that we've been looking at are what are the policies for sharing data in journals, right? So, you know, many organic journals, for example, ask you to supply different types of characterization data along with your manuscript, and often this is in the supplementary information, for example. So when you look at this by different data types, in the yellow boxes there, you can see that's crystallographic data, XRZ diffraction data. There's some pretty long-standing activity there in publishing that data files and putting them in a repository and linking that into your manuscript. I think many of you may be familiar with that if you've published any kind of characterization studies. Ian will be talking a little bit more about that after me. But then when you look at some other data types like the spectra that we were looking at, sure enough, a lot of journals are requiring that kind of data to be included, but it's showing up much more often right in the manuscript or the SI and not as actual separate data files. Up on the upper right-hand corner is a figure from a paper that just published earlier this year. Oh, you zipped ahead, Fatima. There you go, thanks. You know, that's an expanded and updated study version of the same study. You know, and we took a broader look at many more different kinds of data. And, you know, there's been some progress made. The green is sort of more machine readable, native data file formats, et cetera. We've made some progress in ORCIDs. We've made some progress in data availability statements. You've probably at least had to submit your ORCID with your manuscript. Not so much progress on the upper left, which are structure, information, and file formats for different data types such as spectra. So yes, very similar requirements coming in through author guidelines and also as actually reflected in the articles themselves. So we haven't moved the needle much in the last decade, I would say. Go ahead and advance. Just setting up Ian here a little bit because he's going to take a deeper dive into how it works in crystallography. Just wanted to show this. You can imagine on the right side, you know, you've developed your experiment, you write it up into your article, you submit it to the publisher, and then the publisher works with you to review that and get it published. Imagine a data flow where you're doing similar. You're preparing your data files, you're depositing it to a repository, and then you're working with a repository to make sure those data files are all recorded properly, and if there's any links that need to be made to your manuscript or other information. So that's kind of a target view that we've been thinking about as we go through this process, and I'll turn it over to Ian now.
Thank you, Leah. Thank you. So taking an example right now for the standard data files and specifically for the crystallographic information file, the CIF file. Ian, you have been working with the CCDC for decades right now, and you have been working with this data file to add any new chemical crystallographic information to your databases. Would you tell us more about this case of having a very well-established standard file structure for archiving and distribution of the crystallographic information?
Certainly, yes. Thank you, Fatima, and hello to everybody else. Yeah, I have been at the Cambridge Crystallographic Data Centre for a large number of years, and I've been able to see through that the impact that digital data standards have had on workflows. When I joined, structures such as the ones on your screen, we'd sort of code the coordinates of those, and often that involved retyping the coordinates that some other researcher had typed to get them into a table in their article. But things are very different now, and if you go on to the next slide, today we get around 60,000 small molecule crystal crystal structures published each year. The majority of those are associated with one of 16,000 journal articles, although we're starting to see quite a lot published independently of journal articles, which is encouraging. And these are all made discoverable and accessible through index data resources such as the Cambridge Structural Database. You can also look at parallels to this in structural biology with the Protein Data Bank, and also in inorganic chemistry with the Inorganic Crystal Structure Database. But what underpins these workflows is having a standard file format known as CIF, and if you have published a crystal structure or been involved in that, you'll be familiar with it. What's important about CIF though is it's not just how the information and data is laid out in the file, it's the fact that it's structured in a way that each of the data items in there has a very specific definition associated with it. So when it comes to things like the formula weight, it's there's a dictionary underpinning this file format that defines what that should be and the units that should be used, and that applies to all of those data fields in there. And that's quite important for sort of reliably interpreting that data in a machine readable way, being able to search across it consistently. But having the file formats themselves is not enough. CIF format was first published in 1992. It probably took a sort of period of about 8 years to get to a point where around 80% of structures were being published in that particular format. One of the key drivers for that was the adoption of those standards by the software and the tools that crystallographers use on a routine basis. It is now very difficult not to solve a crystal structure and not have your output generated in that standard file format. And so, yeah, adoption by software and tools is a really important driver. Another piece of this is the journal publishers and the data repositories working together to come up with workflows that make it easy for people to deposit their data as part of the manuscript submission process. And then something that I haven't mentioned here is the fact that we have something called CheckCIF, which allows you to check for the consistency and completeness of your data. The Protein Data Bank have a validation workflow, and these become part of the researchers' sort of way of operating to make sure that the data that they've got is fit for purpose. One of the other important enablers I just want to say a bit more about on the next slide is standard identifiers for the various objects involved in research. Now, I suspect many of you will have clicked on a DOI or digital object identifier to access an article or something like that. And we can assign DOIs to articles. We can also assign them to data sets too. But it's not just the identifier and it's not just the resolving mechanism. When these identifiers get created, it's typical to provide additional data alongside those DOIs, particularly about the who's publishing it, where it's being published, and these sorts of things enable and encourage citation of the data as well as the journal, and they also enable us to link those two things together. If that sort of additional data or metadata extends to sort of describe what the data set is about or what the article is about, then that starts to make it possible to interoperate with other systems that may be involved in enabling discovery of information resources. It's not just articles and data sets that we can assign these to, but Elia's mentioned ORCIDs. We can assign IDs to researchers, organizations, instruments, and samples and specimens. There's various schemes out there that allow you to identify those, and we'll talk about how we can apply identifiers to chemical structures. And the more things we can identify with standard identifiers and the sort of capturing the metadata alongside these, we can start to build up sort of networks that allow us to see how all these different objects that are involved in the research process interact and gain new insights.
Thank you, and that's very interesting, talking about the identifiers of each element that is incorporated in research. And thank you for explaining the CIF data file, which is a very well-established one. And I'm now following up with Leah to let us know about the role of IUPAC here as the International Union as actually a global chemistry authority. What do you see the scope of the IUPAC role here, Leah?
Yeah, excellent question. So go ahead, right on to the next slide. So when we think about standards, Ian was talking about, they've standardized the CIF, they've defined it very carefully, they've standardized it, they've defined all of those, the scientific parameters and the syntax that's necessary in the CIF file and to describe those structures richly. This is very similar to what IUPAC has been doing for a very long time. IUPAC is a standards organization. This is the mission for IUPAC, to be the global organization that provides objective scientific expertise and develops the essential tools for the application and communication of chemical knowledge. And by tools here, we mean, those underlying, defining what the meaning and the parameters are for really important chemistry concepts, chemical methods, and this underlies how we can communicate consistently, how we can make sure our measurements are of high quality and consistently communicated and reported. So that's what IUPAC does. It pulls experts from all over the world. There's 2,000 volunteers that work on defining these, and it's a very consensus-based process that's used to do that. Go ahead and go to the next slide. So, how does IUPAC support this? The mission to support these common language? Lots and lots of detail and is important. I mean, Ian mentioned the SIF dictionaries. If you actually go look at them, there's just so many pieces of information that are available that you could use and that are actually useful for further analysis on any of these data resources. So here's just a few of the kinds of things that IUPAC defines. All of these are documented in the openly available standards. Most of them actually still in PDF, so IUPAC is on a very similar trajectory to the chemistry community about sharing our information. But IUPAC defines parameters for units and symbols in chemistry, different models for assessing uncertainty, various notations for describing chemicals. So many of you are familiar probably with the nomenclature. There's also graphical representation standards, so preferred ways of graphically representing compounds. And I'll talk about a couple of the other digital ones in a moment. And then many terms describing chemicals. So one recent one where we've collaborated with BIPM on the SI units, all the SI scientific units were updated not too long ago in their definitions, and we collaborated with them on the definition of the mole. So that was a joint effort, and IUPAC collaborated on that. So we hold that term in our corpus, along with many others that are important for describing chemical data. And they have 100 years. Go ahead.
Thank you for this introduction, and definitely we're going to be following about the digital IUPAC moving from here. All right, before we go to the next question, let's ask our audience actually the second poll question over here, which is, how familiar are you with the efforts of IUPAC to translate standards into the digital domain? How familiar are you to do that? Laurie, if you can. All right, so the poll is now on.
All right, we're starting to see a slowdown in the number of responses, so I'm going to close the poll in 3, 2, 1.
All right, so let me share the results with you here. So we have folks who have never heard about the digital IUPAC at all. So we have 20%. Same percent, which is 20%, they are very familiar, 36% somewhat familiar, and other 20% not very familiar. And the rest of 4%, they are familiar. So we have a variation of folks over here who are either familiar or not. All right, so let us go actually to our next slide and our next questions. And this question also go to Leah. So IUPAC, as you mentioned, Leah, has issued, has a large domain of work around nomenclature and, of course, terminology and chemical representation. And I know, for example, that IUPAC also has issued many colored books of terminology, representation, and critically evaluated data. As you can see here, this is the cover of the Gold Book. And the Gold Book is an example of these resources that depict digital objective objective identifier of each and every definition of a chemical term. Would you tell us more about that and maybe other standards as well?
Yes, briefly. Go ahead into the next slide. All right, great. Okay, so this is a great challenge for us. Yes, as I mentioned, we have over a century of experience refining the rules and parameters in the logic and language of chemistry for all of us. You know, but what about computers? So computers, you know, they're getting quite clever, but they're really not chemists, and they need those same rules that we need to use consistently. They need to have those articulated in machine logic and language so that they can use them consistently. And so this is not necessarily a one-to-one translation always in terms of how humans approach things and computers approach things. So this is the task that we're putting ourselves to develop digital standards in IUPAC. Go ahead to the next slide. Okay. So I'm showing here on this slide 3 of the digital standard projects that IUPAC's been working on that are fairly well established. And there are many, many, many more in progress, which is great. And we'll be talking about alluding to some of those later on today. So for example, the JCamp-DX is a spectral data exchange format that was developed originally back in the 80s. That was a joint project between IUPAC and some other organizations in the community to make a text-based file format that describes data coming from, different data coming associated with spectroscopic data, and actually it can handle raw data as well as XY process data for spectra. And what you're seeing there is actually a screenshot of that data being able to be used in different online programs such as JSMol or JMol to view the structure, to view the spectra right in the browser. So this is really demonstrating how you can actually use that data. It's accessible, it's interpretable. Very easy, and that exchange format has been around a really long time, and it still is possible to read it, and many softwares do. You can actually export it. I think most of the spectra, most instruments still export it as well. The challenge with JCamp is it hasn't had a lot of recent work on it, and so we have some work ahead of us to bring it kind of up to spec, you might say, in the last couple of decades or so. Another one that people may or may not have heard of, and we will be talking about this one a little more depth, is INCHI, which is the IUPAC International Chemical Identifier. This is encapsulating a chemical structure into a canonical string form that can, that can be used to match different forms against different data sets. So any data set that has a structure associated with it, you can generate an INCHI. You can do this in ChemDraw, for example. You can also copy as other kinds of active file formats. We'll talk a little bit more about that. But the INCHI is really helpful because it's like nomenclature. You can compare INCHIs and it will help you organize an index, but it's a little bit more systematic and a little bit more easy for computers to handle than the nomenclature. And then finally, there's the Gold Book that Fatima mentioned. The Gold Book is a compendium from all the other color books, so it covers a lot of different subdisciplines in chemistry. And then it was put online just about 15 or so years ago, and then each term has its own DOI. So just like you're citing other people's papers when you're developing your bibliography, if you want to, if you use any formal chemistry terms, you can also cite them using the Gold Book there. And that the Gold Book is online and it's freely accessible for anyone to search, and you can actually access it programmatically. So for anyone who likes to use scripts to access things, they can do that as well.
Thank you, Leah. Thank you. And I think we have heard INCHI and many others so many times throughout this presentation. And I'm very excited to learn and get the feedback from our audience how actually they are familiar with these kind of digital structure representation formats and identifiers such as the INCHI, SMILES, MOL files, CIF files, etc. How familiar are you with that? So we'll be happy to get your feedback on that.
Okay, just a few more seconds to get your responses in. So if you haven't had a chance to do so yet, please do. I'm going to close this in 3, 2, 1.
Thank you, Lori. So the results of this poll, we have around 60% says yes, and they use them, use at least one of them, and 30% they heard about them, but they never used them, and 8% they have never heard about them. All right. All right, so let's go to our next questions. Our next question is more about the identifiers, and particularly we're going to be explaining INCHI more in details. And we have seen previously, you know, we talked about terminology. We have the DOI for terminology in the Gold Book. We talked a little bit about INCHI, and we are chemists mostly and chemical data user. We love structures, so we want to learn more about the INCHI. Ian, would you like to explain INCHI and introduce it to us, plus other things if you wish?
Yes, absolutely. Thank you. It's interesting to see that so many people have heard of these and actually do kind of use them as well, which is interesting. But I actually want to start with sort of like representations that we're probably all very familiar with, and that is the sort of chemical diagram and chemical names. This is how we have traditionally communicated between ourselves about the chemistry that we're working on, the structures that we're looking at, and they remain important to this day for that very purpose. But when we start to bring machines and informatics systems and databases into the mix, they're not quite so great. And so again, probably going back to the 90s, if not before, actually, people have been for a long time representing chemical structures in electronic forms. And even if you think you haven't used these formats, you quite possibly have, because they'll underpin things like SciFinder and Reaxys in terms of how these allow you to do structure-based search. And one of the kind of most sort of reliable and common ways that these systems represent these structures is as a sort of connection table. One of the most common formats here is the mol file, where atoms of a structure are representatives, nodes joined together by edges that sort of make a mathematical graph that lends itself to searching. Then over time, people have developed more sort of compact ways of representing these things. So we have SMILES, which is a linear notation, which essentially represents that graph. These get used an awful lot in cheminformatics to sort of be able to manipulate structures, process those, make inferences about properties and generate prediction models and what have you. So those are quite important. But a weakness of SMILES is that there's sort of can be more than one way of representing the same structure, and this is where INCHI comes in, because it aims to provide a standard way of a standard identifier for a particular chemical structure. A general point about all of these representation formats, which applies to INCHI as much as any, is that at the moment they work very well for discrete organic molecules. Put a metal into the mix and they, to varying degrees, get less reliable. But this is an area which the wider community is working on to improve. There's certainly efforts going on to INCHI to do that. But just a little bit more about INCHI and why it's important. It allows you to take different but equivalent representations of the same structure, come up with the same string. You can use that string to search across different data resources and link across those, and yeah, it enables linking across diverse data compilations, which may be in chemistry or biology or other areas as well. One of the other facets of INCHI is it has a layered structure, which means that if you want to sort of do comparisons where you ignore stereochemistry, you can do that. And you might sometimes come across an INCHI key, which is a sort of more compact hash of the INCHI string that was sort of introduced just to sort of make it easier to sort of like search, particularly in things like kind of Google and other search engines where the sort of symbols used in INCHI strings might result in unexpected results. And that was the sort of motivation behind the INCHI key, but it's also become powerful in its own right. So there's a brief overview of the structure representations that we use and hopefully why they're important.
Thank you, Ian. And I think we have a short video over here that we should show. We could show it to you. So let me stop sharing my screen.
We have time.
Well, we do have 20 minutes. We can skip it if you feel that the message has been delivered. So we could share this with the audience now, and if you feel like want to learn more about that, we could definitely add it to the chat box so you can have a look over it later. So I think we can move on to the next question. And the next question is actually one of the applications of ENCHI has been now used in in structure, let's say, validation. And one of the projects that the IUPAC is working on is the Word for project, and they have a subcommittee working on project of making a checker or a validator to double check that the structure is right. So for that, Leah, would you like to talk about it more in details?
I'm going to punt this one to Ian.
Yeah, okay.
Right.
Yeah, I'm going to take this one. I think if you can go to the next slide, Fatima. I think, yeah, before I do, it's important to recognise this is the work of people who aren't on this call. It's a small group led by Evan Bolton from PubChem and his colleagues who have been working on this sort of prototype structure validator, because we see people more and more use of these electronic formats that we've been talking about, but you can run into problems where maybe you don't have the representation that you think you do. So here's a question as to sort of like, how can we enable people to have the confidence that their representation is correct? So this is a prototype structure validator. If you look in the top left corner here, you got 4 carbon atoms. If you don't know your SMILES, that is the SMILES strings for butane. And you can load that and you can say submit, and it will tell you whether it recognizes that as a valid SMILES, and it will also give you back some other information about that. And this is presented here in a sort of machine readable form, JSON, which is showing here output that might be used by other software packages. We go to the next slide, we can provide a more complex SMILES string, and this one has inside it the sort of symbols that indicate where there are stereo centers. So does my SMILES string represent all my undefined stereo centers? Hit submit, and if we go to the next slide, it'll come back and it will tell us that we've got 4 defined stereochemistry centers but 1 undefined. So that tells us maybe that our representation isn't quite what it expected to be. And then we can have a look at the depiction of this as well. Coming back to that diagram, we can use generate convert from the SMILES to that diagram on the next slide. And we'll see visually that perhaps we didn't have all the stereo centers that we wanted. And then the final part of this is, let's put something in which we think is a SMILES. It turns out that what we've represented there isn't something that represents a kind of a valid structure according to whatever rules that we might have set up for our particular domain of chemistry. And here is highlighted the fact that you've got 5 sigma bonds to a carbon, which may not be what you would expect, particularly in an organic context. Though if you're into boron chemistry, you might have some point of disagreement there. But one of the aims of these tools is to make sure that you can sort of like provide your own rule sets that define what is valid, and customize those to your uses. That, I think, was the quick run through of the
Thank you, Ian. So this project is still in progress, so definitely we're expecting to have more to come, so stay tuned. I'll also share the QR code for this website for the same validator that Ian just showed you later in the presentation. All right, so that moves us actually to the next question, and this question goes to Leah, which is about describing samples. And I know you mentioned already that samples could be at some point having a digital object identifier as well, and it doesn't seem that it's very straightforward. It's a very complex topic over here. So capturing chemical measurement is dependent on sample, but sample is a complex issue when we talk about data. Sample's origin is wide and varied. It could be a product of a mix of from a synthesis reaction, or the output of a batch process, or collected from a natural environment like soil, water, rocks, etc. Many pieces of information are attached to each sample, like the type, the quantity, the location, the time, the physical state. Is it a mixture? Is it a solution? Is it a pure time of measurement? The analyst, the location, and so on and so on. How do you embed, or how to embed all of these information, or what we call it in the digital domain or in the data domain, the metadata, and report them digitally without losing any.
Yes, that's a great challenge, right? Right. Well, if we all use the same software, then it would solve everything, but that's never going to happen, right? And there's good reasons for different programs. You know, they have different advanced features depending on the kind of science in question you're asking. So we're never going to get to that, you know, one software to rule them all kind of scenario. So that's kind of IUPAC's take on this, is to try to describe what are those core components for just, you know, about the chemistry itself, the system, the sample, the chemical system, the parameters of the measurements, the properties that you're measuring, the conditions that it's measured under, you know, the units that you're articulating and communicating your data in, et cetera. So this screenshot is actually a project we're working on IUPAC to describe the data model behind a compiled set of data, a solubility data series that we have. And that IUPAC critically evaluates. So, you know, I'm not asking you to look at this in detail, and this isn't draft. The point is that this is a group of scientists who are trying to compile data out of the literature and reuse it in a compiled data set. Imagine you're the one publishing that data. You need to make sure that they have all the information that they need to actually then be able to use it and compile it with other data and compare it and do some further analysis on it. So there's a lot of different pieces that are needed to do that kind of thing. You know, in this model, they're emphasizing provenance, they're emphasizing the chemical system, they're emphasizing parameters of measurement. You know, for the provenance, I think you know, that's you and what you've done. Your methods you've been using, and then the system. Fatima talked about the sample. You know, where does it come from? You know, if you've done a purification analysis on it, what phase is it in? You know, what are the different components involved? If it's a mixed sample, you know, and then when you get down into the measurements, you have all kinds of conditions. You know, especially temperature and pressure. Those are probably the most critical ones to capture. You know, and then the estimated error of the temperature measurement, for example, the estimated error of all the other components that all contributes to the system. So it's a lot of moving parts. And some of them are only known by you, and some of them are captured in the instruments that you're using potentially, or they're captured in multiple instruments. So kind of keeping track of all those parts is a real big challenge. Go ahead to the next slide. So getting back to our original workflow here, where I was talking with my chemists about, you know, their workflow to publish their spectra data, you know, where they had all of these different activities that they were doing to collect it from the instruments and the analysis and the process and the supporting information. Imagine as you're going through all of that, everything's being automatically captured into a nice package that has your data, has all your structure files in it already, it has your spectra files, maybe your raw files, your process files, any other data files that you might have taken during that time. It has all the description about your sample and everything in it. And it's all packaged up there. And then imagine that gets deposited to a repository. And you can also generate a description of your supplemental information for interested readers right out of that. That's kind of our target idealized workflow. Again, lots of pieces to keep track of though, lots of different softwares to connect with, instruments and places that files are stored. Happily, there's many different tools emerging, like electronic laboratory notebooks that are emerging on the scenes and becoming better and better every day. So two that are specifically geared towards handling this kind of data, for example, our MBook from Mestre Lab and the ChemMotion from the FDI for Chem project. Those are two notebooks that are available that you know, anyone can sign up and try to use them and see what you think. But I think that's sort of the future trajectory that we're heading, is thinking about publishing data similar to the case around crystallography that Ian was describing earlier, and to publish along with that data all the documentation that you need, and to utilize tools like ELNs to capture all of that and to connect it as seamlessly as we can between different software programs and then the repositories.
That's very interesting, Leah. So we are moving towards having ELN instead of regular lab notebooks. So
it's inevitable.
Thank you, Leah. All right, so that moves us to our next topic, which is about a case of specific data, mainly like the spectral data in general. Ian, would you like to talk about spectral data depiction?
Yes, and I think I should caveat by saying too, a couple of years ago, I'm not sure I would have felt confident enough to address this question, but I've been involved in an IUPAC project which has been looking at the representation of spectra, and I've learned a lot. I think, you know, if we take a simple case, you might have one structure, one spectra, but life's never like that, never like that. You're more likely to have one structure, maybe many spectra, or even maybe many structures that are featuring in many spectra as well. And so you have this sort of complexity of these relationships between structures and data sets. Each of these structures may have come from different samples as well, and so we've got that interplay of sample, structure and data. And then we get down to the data itself. We'll have done analysis on that, and it's important to be able to capture that. And not represented here really is the ideal to be able to capture the steps that have been gone through to sort of collect, process and analyze the data too. And those steps these days are probably likely to be captured in a multitude of proprietary formats. So that's the challenges. In terms of addressing these, on the next slide, I've got a summary of an IUPAC project, which is looking at improving the data management of spectroscopic data. It's working towards a set of guiding principles that will define what it means to be able to publish a spectroscopic data set that is fair. And I'll say a little bit more about fair in a minute. But in doing that, with looking at the data model, that allows us to sort of capture the relationships between the structure, between the data and the sample and the analysis. But importantly as well, thinking about what we term a digital finding aid, which is a term borrowed from the sort of archival community. And what that's going to represent really is the key facets of a data set, what you might also call metadata, but the attributes of that whatever format your data is collected in, however complex that sort of internal data model, that you're surfacing those key elements that can then be used a little bit like Inchi maybe to sort of like have a consistent representation of a data set that can be used to enable searching across resources and interoperability across resources. And we anticipate that this will be complementary to those sort of proprietary representation formats and even the standard exchange formats such as JCamp. And so I think that probably go ahead, Fatima.
Go ahead.
Okay. I mean, that does lead us on to sort of pulling together a lot of what we've been talked to. And on the next slide, I think we're going to talk about encoding best practices through FAIR. I don't know, Fatima, do you want to say something before we go on?
Yeah. So we just heard about the concept of FAIR, and it's a kind of a new term in the domain, the data domain. The FAIR Guiding Principles of Scientific Data Management and Stewardship were released only in 2016, so it's the kind of recent terminology, and were published in Scientific Data. The authors wanted to offer recommendations for enhancing digital assets, findability, accessibility, interoperability, and reuse. What does it mean to have fair chemical data? What is the role of IUPAC in implementing fair data principles? So I think this question might go to either of you, Ian or Leah.
So I'll start, and then I think I'll hand over to Leah afterwards. So if you can go on to the next slide. I think Fatima's spelt out what the acronym itself stands for. I think it's important to note that when these principles were being put together, yes, humans were in mind, but what was driving this a lot was that interoperability of data and that interpretability by machines. And I think the sort of principles came about because almost as a sort of consequence of the success of a drive for more open data. People were putting more and more data out there, and everyone was excited because they thought we can use this in our data science experiments and to build our models, but discovered that that was a harder job than was desirable. And that made people think, okay, what else do we need alongside that data if we're going to publish it to make it reusable by machines as much as anything? And I think we've touched, hopefully, throughout this webinar on the things that contribute to making a data set fair. There are specific kind of criteria that define each of the sort of characteristics, but they essentially boil down to things like standard identifiers, having standard access protocols, using standard vocabulary such as those defined by IUPAC, capturing those in standard metadata schemes such as we talked about with FairSpec, and having the repositories that index these and enable their access. So with that brief overview, I think I'll hand over to Leah to say more about how IUPAC's been helping advance this.
Thank you very much. There you go. Okay, just really briefly, I think Fatima mentioned previously that we're involved in this World Fair project. We are actually with IUPAC leading the chemistry effort there with a focus on standards so that we can help facilitate all those fair enablers that Ian just reviewed. We are actually one of 11 different domain case studies in there. There's others, nanomaterials, geochemistry, and many others. So this is a really huge project. It's being coordinated by CODATA and the Research Data Alliance. And we have 3 target outputs that we're working on through the course of this project. You've already seen a really early prototype version of one of the services we hope to offer through our 3rd deliverable. And we'll be maybe taking, I don't know if we're going to have time to show, we also had a video to show of the 2nd one, a training package that we want to launch in the form of an online cookbook. The idea behind that is that it's an open source. You can go and there will be actionable demonstrations of how you can use data in the cloud, how you can handle things in JSON format, like Ian mentioned, how you can actually connect data sets together and describe them in machine actionable ways. So that's our target for the cookbook. We do have a video. I don't think we'll have time to show it, but we can share that afterwards as well. And then we just republished the first version of a guidance document, which is essentially actually a landscape review of all the different standards that IUPAC and other groups in the community have been working on over time, and a little bit about where we hope to move in the future that we've already been reviewing today. And so that report is just newly available.
Wonderful.
That's
Thank
it.
you. Thank you. And this goes to the final poll that we have for our audience today. We are actually excited to learn from you what kind of help is needed over there for chemists and chemical data users and the data management in the digital domain. What do you think in your perspective?
All right, our answers are slowly coming in, but it's pretty heavily skewed. So I'm going to close this poll in 3, 2, 1.
Thank you, Lori. And I think the majority of our audience just agreed that very much help is needed. 82%, they said it's very much needed. So I think there is a need and necessity over here. And this is the next question for our guest speaker. From where can I get help?
And I think this was going to lead to the cookbook video, because that's just one of the strategies that we're hoping to use. And I did also want to call out that in the World Fair project, we are collaborating with a lot of other initiatives and activities as well. So Ian mentioned PubChem previously. We're also collaborating with NFDI for Chem, which is a national data infrastructure project in Germany to support research data sharing. And they have a whole chemistry project there, and they have a wonderful resources like the ChemMotion ELN that they support, and a knowledge base, so there's support there. There's also the PSDI in the UK, which is a physical sciences data infrastructure project. They're also developing resources. So there's going to become a lot of community resources available, and there's just a lot of opportunity. And we're hoping that as we all learn this and move forward in transitioning our workflows, that we can all share our resources together that we develop in our classes, in our own workflows. And this is part of what we're creating in the World Fair project, are places where we can share those resources. If you just want to show the slide with the QR codes, Fatima, and then I think it's time to say thank you.
All right, thank you, Leah. Thank you, Ian. I think time is finished right now, but if there is any final question from our audience, we will be happy to take it. Maybe we can have a couple of minutes over the time. So thank you for being with us until this moment. I would like to share with you very briefly the QR codes here of our outcomes of the World Fair Chemistry projects. The first code is for the Fair Chemistry Guidance report that we have just launched, and also the cookbook that Leah mentioned several times at this second QR code. Also the protocol services, which is the validator that Ian explained as well. So if you take an image for this QR code, you'll be able to get directly to there. Also, if you are interested to know more about our previous events, we had held a series of webinars titled "What is the Chemical?" So you can also explain multiple topics and get to know about other identifiers and depictions from those webinars. We will be also very busy in coming month, especially in this month of August. We are organizing multiple symposia in the American Chemical Society Fall Data Summit meeting. Also, we will be existing in the IUPAC, and also I would actually encourage you to attend the IUPAC meeting in The Hague if you are interested. The registration is still open. As a Word for a project, we also organizing a symposia in the International Data Week in October, and specifically talking about reusability of data. We will also have a lineup of full workshops, and stay tuned if you are interested to know and learn more about these topics. As an IUPAC person, being involved with the IUPAC right now, I also invite you to check out the ChemVoices past and upcoming webinars. Also, the IUPAC, actually, they launch a quarterly magazine called the Chemistry International. You can check this out as well to get more about an update about the, the projects and the outcomes of the IUPAC. Also, they have a Concentrate monthly newsletter, so you can subscribe for that and get monthly updates about the activities. With that, I've come to the end of this webinar. I would like to finally thank Leah and Ian and Laurie for being here and helping and hosting this event. And thank you everybody for attending. If you have any question, please let us know. I'll follow up with sending the videos and the videos that we haven't shown here, but I will keep a follow up with you regarding that. And if you have any question, please shoot us an email or connect with us over social media, especially Twitter, as well as all of our outcomes of the Word Fair project are there in Zenodo Fair Chemistry community. So we will be happy to have you checking out our work. Thank you, everybody. Thank you.